And intuitively, I would argue it's B. And the reason why is C comes really close to examples. So if these examples are noisy, it's quite likely that by being so close to these examples, that future examples cross the line. Similarly, A comes close to examples. B is the one that stays really far away from any example. So there's this entire region over here where there's no example anywhere near B. This region is often called the margin. The margin of a linear separator is the distance of the separator to the closest training example. The margin is a really important concept in machine learning. There's an entire class of maximum margin learning algorithms. And the two most popular are support vector machines and boosting. If you're familiar with machine learning, you've come across these terms. These are very frequently used these days in actual discrimination learning tasks. I will not go into any details because it would go way beyond the scope of this Introduction to Artificial Intelligence class. But I'd like to say a few abstract words specifically about support vector machines, or SVMs. As I said before, a support vector machine derives a linear separator and picks the one that actually maximizes the margin, as shown over here. By doing so, it attains additional robustness over perceptron, which only picks a linear separator without consideration of the margin. Now, the problem of finding the margin maximizing linear separator can be solved by a quadratic program, which is an iterative method for finding the best linear separator that maximizes the margin. One of the nice things that support vector machines do in practice is they use linear techniques to solve nonlinear separation problems. And I'm just going to give you a glimpse of what's happening without going into any detail. Suppose your data looks as follows. We have a positive class, which is near the origin of a coordinate system, and a negative class that surrounds the positive class. Clearly, these two classes are not linearly separable because there's no line I can draw that separates the negative examples from the positive examples. An idea that underlies SVMs that will ultimately be known as the kernel trick is to augment the feature set by new features. Suppose this is x1 and this is x2, and normally x1 and x2 would be the input features. In this example, you might derive a third one. Let me pick a third one. Suppose x3 equals the square root of x1 square plus x2 square. In other words, x3 is the distance of any data point from the center of the coordinate system. Then things do become linearly separable. Plotted just along the third dimension, all the positive examples end up to be close to the origin, and all the negative examples are further away. And the line that's orthogonal to the third input feature solves the separation problem. Mapped back into the space over here is actually a circle, which is a set of all values of x3 that are equidistant to the center of the origin. Now, this trick could be done in any linear learning algorithm, and it's really an amazing trick. You can take any nonlinear problem, add features of this type or any other type, and use linear techniques and get better solutions. This is a very deep machine learning insight that you can extend your feature space in this way, and there's numerous papers written about this. In SVMs, the extension of the feature space is mathematically done by what's called a kernel. I can't really tell you what it is in this class, but it makes it possible to derive very large new feature spaces, including infinitely dimensional new feature spaces. These methods are very powerful. It turns out you never really compute all those features. They are implicitly represented by so-called kernels. And if you care about this, I recommend you to dive deeper into the literature of support vector machines. This is meant to just give you an overview of the essence of what supported vector machines are all about. So in summary, linear methods, we learned about using them for regression and also classification. We learned about exact solutions versus iterative solutions. We talked about smoothing, and we even talked about using linear methods for nonlinear problems. So we covered quite a bit of ground. This is a really significant cross-section of machine learning. As the final method in this unit, I'd like now to talk about k-nearest neighbors. And the distinguishing factor of k-nearest neighbor is that it is a non-parametric machine learning method. So far we talked about parametric methods. Parametric methods have parameters like probabilities or weights, and the number of parameters is constant. Or put differently, the number of parameters is independent of the training set size. So for example, in the naive Bayes, if we bring up more data, the number of conditional probabilities will stay the same. Well, that wasn't technically always the case. Our vocabulary might increase, and as such the number of parameters. But for any fixed dictionary, the number of parameters are truly independent of the training set size. The same was true, for example, in our regression cases, where the number of regression weights is independent of the number of data points. Now this is very different from non-parametric, where the number of parameters can grow, in fact can grow a lot over time. Those techniques are called non-parametric. Nearest neighbor is so straightforward. I'd really like you to introduce using a quiz. So here's my quiz. Suppose we have a number of data points. I want you, for one nearest neighbor, to check those squared areas that you believe will carry a positive label. And I will give you the label of the existing data points. So please check any of those boxes that you believe under one nearest neighbor carry a positive label. And the algorithm, of course, searches for the nearest point in its Euclidean space and just copies its label. And the answer was, this is a positive point and this is a positive point. These 2 points over here are negative. So let's define k nearest neighbors. The algorithm is really blatantly simple. In the learning step, you simply memorize all data. If a new example comes along whose input value you know, but which you wish to classify, you do the following. You first find the k nearest neighbors, and then you return the majority class label as your final class label for the new example. Simple, isn't it? So here's a somewhat contrived situation of data point we wish to classify, where the labeled data lies on a spiral of increasing diameter as you go outwards. Please answer for me in this quiz what class label you'd assign for k equals 1, k equals 3, 5, 7, and all the way to 9. And this is easily answered. The nearest neighbor at this point over here, so for 1 we say plus. For 3 neighbors we get 2 positive, 1 negative, it's still plus. For 5 neighbors, 1, 2, 3, 4, 5, we get 3 negative, 2 positive, it's a minus. For 7, we get 3 positive, but still 4 negative, so it's negative. And for 9, the positives outweigh the negative, so you get a plus. Obviously, as you can see, as k increases, more and more data points are being consulted. So when k finally becomes 9, all those data points are in and make a much smoother result.